So I'm going to talk about zero-knowledge proofs in this session. So this is going to be a talk about cryptography and kind of new cryptography. So today we all use encryptions and signatures and so forth in everyday applications to ensure security and privacy. But sometimes we want to have applications where we care about both the privacy of data on one hand, but also to show that or to prove to the world that it satisfies certain properties or is well formed or have some kind of integrity to it without revealing the data itself. Okay, so it's kind of a view into recent research development that is coming and that might have some interesting applications that you maybe can use in your situations, organizations going forward. So I'm going to talk a bit about what kind of use cases, how this works, some tools you can start playing around with for maybe something interesting in the future. First, a few words about myself. I'm an associate professor at NTNU working in cryptology, and I'm leading the lab we have at NTNU working on these topics. My own research is about quantum-safe cryptography that you might hear more about tomorrow if you attend my workshop. I'm also working on different privacy applications, which is related to this topic, and also secure implementation of these protocols. I'm also working part-time as a cryptography expert at the startup Pwn Biometrics here in Oslo. Okay, so as I mentioned, we use cryptography today, and we can roughly divide them into three categories. So on the top left, we have public key encryption. Okay, so you have some kind of public key that is available to everyone in the world. You can use this key to encrypt a message, to generate a ciphertext, and this can be sent over an insecure channel to the owner of the public key, and they are the only one who can decrypt. So this is usually used for key transfer today, where you want to talk to someone, you generate a key, and then you send this to the recipient, and then you can use this shared key to communicate further. So that's the middle on the right, where you have a symmetric key scheme, for example, AES, where you have a shared key, and you want to send some application data, some messages, and you use this to encrypt it. Okay, and you can do this because you already have the shared key using the public key encryption scheme first. Yeah, so this is often how it works in TLS and Signal and most applications today. So this gives you confidentiality. Yeah, you protect the data itself. But sometimes we want to know that no one messed with our ciphertext or changed it or replaced it, and also that we know where the data is coming from. So then we need the primitive on the bottom left, which is the digital signature. So there you have some kind of message. This could be a software update, it could be the ciphertext that you just sent, or something else. You hash this down to a fixed sized string, and then you sign this using a private signing key. Yeah, and there's a public verification key that everyone knows, and they can check that the signature is valid, and then you are certain that the data that you received has integrity, so it didn't change, and you know where it came from, because there was only one person who could sign this. Okay, so these are the three most common primitives we have available today for secure communication. And there's so many applications that use these under the hood, and you probably either have used or know of most of these, but secure messaging is a very common application. A lot of people use Signal or WhatsApp or iMessage for communicating. You have secure connections to websites, servers, and so forth, using TLS or SSH or IPsec. You have digital authentication. A lot of the community is kind of switching over to FIDO for secure authentication instead of passwords. We have bank ID and other services in Norway where you can use this to log into government services and other things, and as well as different payment systems. Okay, so this is kind of the most common things. But then a natural follow-up question is, what else is out there? What can we do? What kind of research and development have taken place and is kind of ready-ish for new applications to be deployed? So we're going to talk about some of them, and you often have this kind of relationship between privacy and integrity where it seems hard or impossible to achieve both at the same time. So often you have users who have some kind of private sensitive information. It could be their identity if they have an authentication platform. It could be a vote in a voting system. It could be a transaction and so forth. So you might have some sensitive or private data that you want to keep secret from others, but you sometimes still want to maybe apply this kind of data in some machine learning algorithm or to authenticate yourself to some server. And you want to then on the server side know that this information is valid, it's correct, it's something you can trust. Okay, so the classical example there would be the newly discussion about age verification. Yeah, so then if you want to log into some system, you need to be, say, 18 years old to access it. And the server need to know this because otherwise they might be penalized or fined or something. Yeah, and the way they do it is often by asking you to give over like a passport or identity card or something, which is not just saying that you're more than 18 years old, it's also saying a lot about you. It might be your date of birth, it might be your address, a lot of sensitive information. Okay, and this we don't really want to share, and it's not really what's asked about. We only need this binary value saying if you're below or above 18 years old. Yeah, we're not really asking for your whole identity, but that's the only solution we have for it now. So this is a problem that we would like to solve, where we want to kind of achieve some form of data sharing without breaking the privacy for the user side and also still ensure integrity on the server side. Yeah. So the solution to this is zero-knowledge proofs. So we're going to talk about what these proofs are and what kind of application we can or are already using them. So when we think about proofs, the first thing that comes to mind usually is some kind of mathematical proof. You want to ensure that some statement is correct. Yeah. So you present that, well, this is kind of the area in this square and so forth have some certain relations. So this is the Pythagorean theorem. And you can kind of prove that this figure on the left is equivalent to the figure on the right by kind of measuring and swapping pieces, and then you can convince someone that this statement holds. Yeah, and this is a quite simple statement, so this we can draw, but we also have a lot of more complicated statements. For example, Fermat's theorem, where you have this famous equation that for some integer x and integer y and z, this relation does not hold if the exponent n is larger than 2. And we were able to prove this, or Andrew Wiles in this photo was able to prove this some 20 years ago. Yeah, but the proof of this statement is so difficult that just a handful of people in the world can understand it. So we are convinced about this truth by proxy, because we have someone else kind of verifying on our behalf that this statement is true. Yeah. So also in mathematical proofs, we write it down. Yeah, there's no really private information. It's more about you have some statement or something that you claim, and then the witness or the proof of this is by describing, why this is true, or giving some information that you can check that the statement holds. But in zero-knowledge proofs, this is also some kind of, say, interactive protocol between two parties. You have a prover and a verifier, and you want to convince the verifier as a prover that some given statement is true. Yeah, and you are allowed to communicate back and forth, maybe 2 messages, maybe more. And at the end, the verifier should be convinced that the statement holds. Yeah, not necessarily by you providing the sensitive information that obviously shows that this holds, but through this communication, they should be convinced of this claim. And for these kind of protocols, we have 3 properties. So the prover publishes some statement or some claim, and we're going to talk about more like what kind of concrete claims can be made. And they keep a secret witness, which shows that the claim holds. And for this communication or for this protocol, we want it to be correct. So if the prover actually holds a valid witness, say if you have a passport that says you are more than 18 years old, then if you follow this protocol, then the verifier should accept it in the end. Yeah, so you can have some described communication. If you follow this plan, then you will end up with the verifier accepting if you hold the witness. So that's the correctness statement. And then we have something we call soundness, which essentially means it should be difficult or basically impossible to cheat. So if you don't have this witness, say if your passport actually says you are below 18, you should not be able to convince the verifier that you are above. Yeah, you should not be able to convince someone of a false statement. So that's the soundness. And finally, in the end, and this is the privacy property of these protocols, is the zero-knowledge protocol, yeah, or the zero-knowledge property. And this says that if you complete this protocol by communicating back and forth, the verifier is convinced that a statement is true, but it doesn't learn anything whatsoever about the witness that proves that it's true. So for example, they are convinced that you are above 18 years old, but they don't learn anything about your passport. Yeah, only this binary value saying, yes, you are above. Yeah, and nothing else. And this is often what we want. We often give a lot of extra information to convince someone about something, which is much more than what they actually need and what we often would like to provide. Yeah, so this says we can design these protocols where this information, this bit, is the only thing that the verifier learns. And that was the goal of the protocol, and everything else is still secret. And this was actually introduced quite some years ago. So Goldwasser, Mikhaly, and Rakov published a paper about these proof systems in the mid-80s and have later won a Gödel Prize for this, which is kind of like the Abel Prize or the Nobel Prize, but in theoretical computer science. So this kind of laid the foundation for achieving these things, but they're quite theoretical, abstract, and have been without clear use cases for a long time. So we're finally there, where we have a lot of interesting use cases and implementations and applications where these might make sense to start being used today. So that's what I want to talk about today and why I kind of submitted this topic, because it's something out there that is very interesting, that very few people know anything about, and it might open a few doors going forward. Yeah, so let's talk about some of these opportunities. Well, okay, one final thing about these proofs is that, well, I draw the picture of a zero-knowledge proof where you have a protocol with two parties talking, yeah? And we might have a protocol that is interactive, where you're actually sending messages back and forth, maybe several rounds. But you could do it in a non-interactive way as well, where you just write down this zero-knowledge proof once and for all and send it. But in general, you might have an interactive protocol where in the mathematical proof, you do always write down, all the details about why this is true. For soundness, well, in a mathematical proof, we would like it to just always be true, like either the proof is true and everyone can accept it, or it's false and no one does. In zero-knowledge proofs, we do allow for a small cheating probability, but you can usually control how likely it should be to cheat. And you can basically say that this is, as hard to cheat in this protocol as breaking AES or breaking the RSA scheme that we use in other cryptographic protocols. Okay, so it's not impossible. It's just as hard as breaking cryptography in general. And one interesting thing that I'll also bring up closer to the end is that if you have a mathematical proof, you need to describe everything. Yeah, you need to be able to follow it step by step and understand why this is true, and the proof might be very long. But in zero-knowledge proofs, you can sometimes have proofs, in terms of, bytes that you're sending, that is much smaller than the witness for your statement. Okay, so you're actually saving space by producing this proof, not only giving privacy. Yeah, so we'll get back to that. Okay, so let's talk a bit about potential applications of zero-knowledge proofs. So this is something that is already deployed and is out there, and you might have other related applications in mind for your own situation. So one thing is actually quantum safe signatures. So as you might be aware, we are currently migrating to from normal digital signatures that I mentioned in the start, based on factoring and discrete log assumptions, for example, using the RSA scheme or ECDSA. These are the most two common digital signature schemes today. They are not secure against quantum computers, so we need to replace them with something that is. And one way to build such signature schemes is essentially by using or building a zero-knowledge proof of that I know a secret signing key that corresponds to this public signing key. And the first standard that we have available, FIPS 204, which is the ML-DSA signature scheme based on lattices. This is in reality a zero-knowledge proof of that a secret signing key, which is now standardized as a digital signature scheme. Okay, so what you can have is this protocol. So I'm not going to go into detail of it, but if you're interested, I'm going to talk more about this tomorrow. But essentially, you have two vectors that are secret, and are all the coefficients in these vectors are small. Think binary. And then you have a public matrix, and you compute the product between these vectors and this public matrix, and that's your public signing key. And then you're able to sign a message by sampling some randomness. So the prover is sampling some other vectors and compute a matrix vector plus vector product. Okay. It sends it to the verifier. It gets some kind of challenge, which is just a random value to kind of challenge the prover. And then the prover answer with something that is related to the randomness, the challenge, and the secret. Yeah. Again, I'm not going to go into details. And this is also how discrete log signature schemes works today. And then there is a response in the end. So there's some back and forth. Yeah, that's the goal. And then you check if the some equation is verified in the end. Yeah. If this equation is verified, then you accept this proof. If not, you reject it. And the goal here is that you are only able to produce a valid proof if you know these secret vectors S1 and S2. If not, you're not able to convince anyone about this. And we can transfer this into a signature scheme by, instead of having a verifier that sends something back, you hash everything you would send in the first message together with the message that you want to sign. So this W value and the message is being hashed. And then you respond with both this hash and the response in the last message. Okay, and then you have a signature scheme which is only one message instead of back and forth, and it's tied to a message that you want to sign, for example, a code update or a ciphertext or something else. Yeah, so we can create digital signatures from zero-knowledge proofs, where the statement is, I know a secret key that corresponds to this public key. So this is actually the most common way today to design signature schemes. So this new standard is already an application kind of under the hood of zero-knowledge proofs. Another application is electronic voting. So we don't do that in Norway, but a lot of other countries have elections where you are able to vote from your own computer. And then we need to know that whenever a vote is submitted, that this is correct. So, for example, if you provide a ciphertext into the voting system, you need to prove that this is a valid vote. And then you can use a zero-knowledge proof saying that here is a ciphertext, and here is the list of all possible valid votes. And you prove that one of these votes, without saying which one, is encrypted in this ciphertext, so this should be counted. And then you protect the privacy of the user because you don't reveal what this specific user voted for, while the voting system can be sure that this is actually a valid vote, so that it's well-formed and it can be counted later on. Often we shuffle votes in a voting system, so think of the physical ballot box. If you shake it a bit to make sure that the order of votes are, when you pick it up, is different from the order when it went in, so that you cannot make the connection between who voted and their vote. And we have a digital way of doing this as well, where you have a bunch of ciphertexts, and then you re-randomize them, essentially by adding an encryption of 0 to it. And then the ciphertext looks different, but it's still encrypting the same value. And then you permute them. Yeah? And if you do this, we want to ensure that no one swapped a vote with something else. So then you also need a zero-knowledge proof, which says, I re-randomized them in an honest way, and I permuted them, and I did not replace any of the votes. Yeah? Then you get privacy of the permutation and the re-randomization, and you get integrity of the permutation. Then everyone else can trust that this is still the same voting set. And finally, you need to decrypt it. And of course, you don't want to give out your decryption key to the world. Yeah. So what you do is you decrypt all of the ciphertext, and then you prove that I used the correct decryption key to decrypt all of these ciphertexts, and then you can look at the votes yourself and count it in the election. Okay, so this is a very important building block to ensure both privacy and integrity in electronic voting systems. Yeah. Another application is anonymous transactions. So for example, you want to pay someone, but you don't want anyone else to know how much you paid, or which account it went from, and which account it went to. And this is, for example, possible in one of the cryptocurrencies called Zcash. So what you do is you encrypt your transaction, the sender, the receiver, and the amount. And then you prove that the sender, whoever that is, have this amount that is not disclosed available in their account. So this is a valid transaction. You actually do have the funds that you're trying to send. And you prove that these funds are not spent, otherwise. Okay, so you want to make sure that this is a valid transaction. You're not creating money out of thin air. You're actually using money that you own, and you're sending it to someone else. Yeah, so then you get privacy of the transaction, but you do get integrity in the payment system. So this is how this could be done. So you have this red box, which is like all transactions in the network, all the addresses, and so forth. And then you can have a top layer, which then encrypt the transaction, prove something about it with respect to the public ledger. You might have other properties you want to prove as well. For example, that this satisfies some regulations or something like this. And then you can get both shielded address, shield for sending, for recipient, and for the amount being sent. And this is actually implemented and used today. Okay, and another interesting application, and this was kind of my motivating example to begin with. We want to have what we call anonymous credentials. Yeah, and one regulation that is coming is the EU Digital Identity Wallet, where we have a digital wallet containing information about us. It could be connected to funds or tokens in some way, but it's also about our identity and properties about us, like where we live, nationality, date of birth, and so forth. Information about us that might be interesting to prove something about or to show to get access to certain applications. So for example, in this setting, you would have some issuer, which might be a passport department, which in Norway would be the police. You have some kind of training program, university, other public services like your driving license and so forth, which can issue some credentials on your behalf. Yeah, so they need to know who you are, but that doesn't mean that they should know anything about how you use your credential. Yeah, that's your business. So you ask for this, you get a credential, and you hold it. And then you might have a lot of services that you want to access, either related to online shopping, some bank services, some login, some availability, some kind of age verification. There's a bunch of things where you would usually provide a copy of your passport or similar to get access to, where they don't really need all of this information. They just need to know that you satisfy certain criteria to get access to some given resource. And then this credential holder can then, instead of providing the passport, you can give a zero knowledge proof. So this could be, for example, I hold a passport which is signed by the Norwegian police that says my date of birth is earlier than one given value that says I'm above 18 years old. Yeah. So then the verifier learns that you are meeting the threshold without learning anything else about you. So we can control what kind of information we release. We don't need to give it all. This was actually in a simplified version implemented in the Norwegian contact tracing app during the pandemic, where we wanted to have a disconnection between the owner of the app, which then collected where they had or who they had met, and when they were uploading data to a backend service for notifying the people they have met in case of a positive test. Yeah, so we thought this was an important privacy issue that we need to solve. We did not want to tie everyone to everyone they had met. And so then we had an app which logged into some verification service. So in Norway, this was a service that have on a national level overview of all positive corona tests. And if you had a positive test, you would get some token that is a kind of a certificate on that the test is positive. So this was important so that no one could, say, spam the system by sending warnings to people who had not really been in touch with someone who tested positive. Yeah. So we wanted to avoid that, so we needed some kind of verification. But then you would later upload what we call these contact tracing keys, which are keys that you negotiated or exchanged with everyone that you were nearby. So you would have some kind of value that you could share to a backend service, and this service could check the certificate you got from the verification service and then warn all of the users. And basically by sharing these keys, and then you could check locally, do I have a copy of this key? If yes, then I have been nearby this user. If not, I'm okay. But what we did then was to randomize this token. So this app, it could receive a valid signature or a certificate, and it could randomize it, but only once. Yeah, so you could create one new valid token when you received this certificate. And this token was unlinkable to the signature or the certificate that you received. So one, you knew that it was valid. Second, it could not be tied to you. And then we had also to use zero knowledge proofs to prove that this was a valid token and it was signed properly and so forth. And this ensured that we could get both privacy and integrity in the Norwegian contact tracing system. So this was a one-time token, but on the previous slide, if you have general anonymous credentials, you could even log into the same service many times and always provide proof saying I'm a valid user without these proofs being linkable. Yeah, so even if you log into the same service 10 times, for the server side, it looks like 10 different people that are allowed to use this service are logging in. They cannot tie it to one user. Another interesting application is verifiable machine learning. So today we are using, more and more services are looking into how can we learn something from a lot of data by using machine learning. And then either you need to train it and create your model, or you have a model and you want to evaluate something to get the result. Yeah, and often the data being involved might or be sensitive. For example, if we want to either train or evaluate health data, yeah, then we need to care about the privacy of the patients and so forth. So what we often do is that we have some service, and you want to know that the input data to this service is valid. But often this input data is private, so you don't really want to share it with, say, Google or some other service. While Google or this other service, they own the machine learning model, and that's their IP, and they don't necessarily want to share their model because that's how they make money. So you kind of still have this privacy integrity challenge where you want to ensure that everything was done correctly, but you still want to both keep the data from the service and the model from the client. So what you could do, for example, is that if you have a machine learning model, you want to convince the world that this is trained on specific data so that you know that this model is something you can use, that it's trained on relevant data. Then you can prove without revealing your model, you can prove that it was actually trained on this data. Or you could prove that this model that you have, this is evaluated on a specific set of data. So it's not garbage that is coming back, you actually used your model, and that's the service that you get paid for. Yeah, and this data that you get in could potentially even be encrypted, so that you never actually see the data you are either training on or evaluating, but you prove that you did it correctly without revealing what you did. So these are quite interesting applications nowadays because for now you basically need to trust the service that are involved in either the training or the evaluation of the data. Furthermore, we have what we call succinct arguments. So there's a kind of a special class of zero knowledge proofs which are designed to be specifically efficient. So this kind of acronym of ZK-SNARK means zero knowledge, succinct, non-interactive argument of knowledge, where the zero knowledge part is what we have talked about so far, that you have some secret witness that does not leak when you produce the proof. Then we have the succinctness part, which means that the proof is very fast to verify and very small to send. It's non-interactive, so you don't need this communication back and forth. You could just publish the proof online once and for all, and everyone can verify it. And the last two about argument of knowledge just means that you know the witness. So it's more like a fancy acronym for that. And in this case, we would like to produce proofs that are much smaller than the secret itself. So for example, if you're outsourcing some computation, say a machine learning model, this might be very computational intensive to evaluate. right? We often need computing clusters to do this. And if checking the proof was as intensive as doing the whole training yourself, this is not something that people in general could verify because they don't have the resources. Or it could be some large, complicated statement. It could be a transaction. It could be some relation in a voting system. It's a lot of data. It might not be possible for everyone to validate it. And then you would like the proof that you check to be much, much smaller than if you knew everything about the system. So often we talk about these proofs being very small, either logarithmic, so that it's very small, but it does increase a bit if the whole system increases, or even constant. And we do have proof systems that are constant size, which means no matter what you want to prove in the world, the proof is 1 kilobyte. Okay, it could be very simple, like I know the secret key, or it could be, you know, a very complicated large statement about some machine learning model or whatever. So no matter what you want to prove, the proof size is 1 kilobyte, always. And the verification has to be much faster. So this could be, you know, milliseconds, even if the proof took hours to produce. The downside of it, of course, is that we're kind of shifting the effort to the prover side. So those who want to prove something complicated also need to spend more time and memory of actually producing the proof. But this means you could have a powerful server proving some interesting statement, while you could have a mobile client verify it afterwards, and the whole system is something that they would never even fit on their mobile device. But they can still verify that something was done correctly. So this is an interesting kind of special kind of proof systems that is also possible, even though at least my intuition says that this should not be possible. But we can actually do this. So where are we today? Well, so this has been kind of an ongoing research effort for many, many years, and we do have all kinds of systems out there, and I showed you some examples. There is some standardizations effort now to kind of make this available for others so that you can kind of use this throughout systems and you know what to use in certain applications and so forth. And NIST is currently having a process about this to kind of collect proof protocols out there and try to generalize them and standardize them so that we know exactly how to implement it in a secure way for certain applications. So this is ongoing right now. There's also some more like industry consortium which are looking into it for their own applications. Like the ZK Proof community, there's the Ethereum Foundation for the blockchain applications and so forth. So these are kind of all trying to write up standards or standard-like documents so that things are consistent across systems. But in general, there's not, you know, something ready yet, and it's kind of a ad hoc as far as we know. So this is, I think we'll see a lot of progress here in the coming years, especially when the EU wallet regulation is final. Then they also will have to somehow standardize what kind of proof systems you are supposed to use for the anonymous credential situation. So this is coming, and it's kind of an opportunity now to get a bit ahead of it and see where this can be useful for your work. There's a bunch of open source libraries out there. You will find a lot of the things that are actually in deployment today, but they're quite complicated. So I tried to find some libraries that are open source and designed for educational purposes. So not really for production systems, but to kind of play a bit with to get some hands-on experience with what these proof systems can do and not, and how to use them. And then there's, these ones like Baby Snark, which is written in Python specifically to learn about these systems. You have ArcWorks, for example, that is also used in Zcash, among other systems, but it's kind of high level and should be possible to do something interesting without too much effort. But in general, here are 4 projects, and there are more online if you search for it, or maybe you have a certain application in mind, you might find something that fits you. But in general, all of these systems that we develop, they're usually open source. So this is something that you can look into if you're interested. And finally, I want to say a few words about the larger context. So zero-knowledge proofs is one out of several privacy-enhancing cryptography techniques that we have developed over the last, say, 30 years. So here you can prove things, right, without revealing the secret itself. You have other techniques that are also being developed. One is fully homomorphic encryption. This means that you can encrypt your data, but you can apply functions to the ciphertext as you would do with the data itself. Yeah, in general, you cannot do this. Yeah, so if you have AES ciphertext, if you flip 1 bit, the ciphertext is useless. Yeah, but you do have systems that are built so that if you want to compute additions or multiplications or other functionalities on the data, you can actually do it directly on the ciphertext, and the function translates to doing this function to do this operation on the underlying message. So then you can do outsourcing. For example, if you have health data, you might encrypt everything. You can send it encrypted to some service that have a machine learning algorithm. They can evaluate this algorithm on the encrypted data, and you get the result back. You can decrypt it with only the result. And they didn't learn anything about your data. Of course, then this can be used in both with zero-knowledge proofs and fully homomorphic encryption, so that you keep the privacy of all the data while it's being computed, and you can prove that you evaluated the machine learning algorithm on these ciphertexts. So these are often used in combination, where the fully homomorphic encryption protects the input data, and the zero-knowledge proofs prove that the integrity of the process is satisfied, and also protect the machine learning algorithm. Another application or technique is multi-party computation. In the previous one with fully homomorphic encryption, you usually have 2 parties. So one is kind of the data owner and one is doing the computation. But often you have multiple parties who would like to jointly compute some function. This could be that you all have, say, salary statistics for your company. You don't want to share those with others, but you would like to generate statistics among all of you. And then you can, without revealing the input data to the other parties, you can all generate some statistics about the joint data. Again, you are often using zero-knowledge proofs in these systems to ensure that everyone is behaving honestly in the process. So again, these are kind of techniques that also go well together. And that was what I had for today. So thank you, and I'm happy to take questions. Anyone? No? That's fine. If you have anyone or want to talk to me, I'm still around. And otherwise, I hope to see some of you also tomorrow for the sessions about quantum safe cryptography. So let's end here.